So, thank you very much, Gilbert, and also I'd like to thank Christopher Lillotte, both of them, for inviting me to come and talk to you. So, I've slightly modified the title, but basically I'm going to talk about thermal conductivity, and I want to give you some idea of some of the work we've been doing in Limoges over the last 10 years on heat transfer. And what I'm going to do is try and bring out the aspects that at the nanoscale could affect thermal conductivity in particular. But I'm going to just do something just slightly broader than that. So I'm going to start with a little bit of general background on thermal properties, remind you of the heat equation, underline the importance of lattice vibrations for heat transfer in solids. Then I'm going to look at dense ceramic oxides and the role of grain boundaries. And then we're going to look at porous materials, and in particular how we can look at this using the two-phase mixture problem. And then I'm going to just finish up with 3 examples where I want to try and bring out what the aspects of features at the nanoscale might do on the thermal properties, in particular the thermal conductivity. So, just to start, thermal properties are generally regarded as being the heat capacity, the thermal conductivity, and the thermal expansion or contraction. I'm not going to talk about the third one. I'm just going to restrain myself to heat capacity, which is basically the energy required just to increase the body temperature, and then thermal conductivity, which is concerned with heat transfer through a system. So we find both of these parameters or properties in the heat equation in terms of lambda, which is the thermal conductivity. And then if you look carefully in the thermal diffusivity, it's defined as lambda over rho c, where rho is the density of a material, and c the heat capacity per unit mass. So these 2 parameters control the temperature distribution in a system, and obviously heat capacity has another role. You need to know how much, if you're looking at processes, how much energy is required to actually fire a ceramic or make a process operate. So if we look just briefly at heat capacity in a solid is basically dominated by lattice vibrations. So we can use the well-known Debye model, which describes how the heat capacity varies with temperature. It starts at basically 0 at absolute 0, and then increases to a constant value, which is the classical limit. Okay? So the region of strong change of heat capacity with respect to temperature is determined by a parameter called the Debye temperature. Okay? And the Debye temperature is basically related, it's a character of the material, the solid. It's related to basically the rigidity of the crystal structure. Okay? So heat capacity determined by lattice vibrations, and then I suppose you should also consider that you can have a small additional contribution coming from defects which form at high temperature, but this would only increase the heat capacity by 2 or 3%, maybe at 700 degrees Celsius. So the nanoscale formation of defects would be a small effect. Since some of you are interested in nanocomposites, so you're mixing up 2 different materials, if you want to estimate the heat capacity, you can use, to a very useful approximation, the rule of mixtures. So I've just, let me see if I can find how this works. Oh. you can just use the rule of mixtures, this very simple approximation here, on using the mass fractions of each component in the composite. Now, lattice vibrations not only control the heat capacity, they have a very important role for heat conduction. So if we just remind you of Fourier's law, the thermal conductivity is basically the constant of proportionality which you find in Fourier's law, in other words, which determines the heat flow under a thermal gradient, so dt dx. Now, the thermal conductivity in a crystalline solid can be considered as a phonon gas. So this is considering the lattice vibrations, okay, which are collective excitations of atoms in the solid, as being having a particle-like character, and then you consider these particle-like entities as a gas. So you can then apply kinetic theory of a gas to obtain an expression which involves the heat capacity at a given frequency, the group velocity for vibrational propagation, and a very important factor, which is the mean free path. Okay? So these are the three factors which control thermal conductivity, and often we will make a simple approximation where we assume that the vibrational propagation speed is basically a constant. In other words, the speed of sound, the low frequency limit. Now, to highlight the role of the mean free path in this affair, if we can compare a crystal to a glass. So in the temperature range of interest, typically let's say minus 200 degrees C to 800 degrees C, the mean free path decreases. And this is because it's the mutual interference of the lattice vibrations, or the phonons, amongst themselves, which increases statistically as we increase temperature. So what we see is a steady decrease in the thermal conductivity. And this is basically due to the strong decrease of the mean free path. Not very good with this beast. So maybe I'll try the other one. Okay. Ah, much better. Okay. Now, it's interesting to compare the thermal conductivity of a crystal material, or a crystalline material, to a glass, because a glass obviously has no long-range order. And here, the mean free path is very short. It's basically that of the atomic separation. So what we now see is that since the mean free path is constant, all we see is a slightly steady increase in thermal conductivity, which simply resembles the heat capacity. So, having given you a little bit of background, I'm now going to move in the case of dense ceramics. What is the effect of grain boundaries? Because grain boundaries we can place at the nanoscale if we try hard with our ways of preparing ceramics. Well, Berman in Oxford in 1952 did some very nice work on alumina and basically compared polycrystalline alumina to the single crystal form. Here is the single crystal, and here is the polycrystal. What you can see is that the single crystal at low temperature has a much higher thermal conductivity. Well, this is again the role of the mean free path. The mean free path here is controlled simply by the grain size. In other words, the separation between grain boundaries. So the grain boundaries scatter the lattice vibrations. Okay? What happens at higher temperature? Well, here we compare two different polycrystalline ceramics plus a single crystal, alumina again, and here you will see in this range of temperature range, about 300 degrees C, is that there is virtually no difference for material with a change of grain size, average grain size, of about a factor of 2. So this is because the mean free path is much shorter than the grain size. So the phonon-phonon interactions are controlling the thermal conductivity, and we see very little difference. Well, the question we could ask is, well, is this simply because we can't see the effect of the grain boundaries, or do they have no effect whatsoever? Just before I leave this slide, I'm going to just mention another very interesting effect. The single crystal, compared to the polycrystalline ceramics, you will see that at higher temperature, there is a higher effective thermal conductivity. Well, this is a radiation effect, so we've just been hearing about the semi-transparent character of many dielectric solids. Well, here we can see this is basically a radiation contribution, and the effect of the grain boundaries is to attenuate this radiation contribution. So here is an effect of grain boundaries stopping basically infrared radiation going through the crystal. So since my data came from Kingery, which showed basically 10 micron grain size ceramics, I'm now going to consider the case of, well, knowing the fact we now often make ceramics with 1 micron size, 100 nanometer grain size materials, do we still have no effect in ordinary temperatures? Well, I'm going to suppose that the effect of a grain boundary is to increase locally the scattering of the phonons, the lattice vibrations. So this would lead to a very restricted, perhaps over 10 angstroms, 20 angstroms, decrease in the thermal conductivity. We can model this simply as a series of resistors. So this is using an idea which comes from impedance measurements and electrical behavior of materials. So we're going to take this model, and then we're going to test it in the following way. We're going to make oxide ceramics with different grain sizes with approximately the same relative density. We're going to count the number of grain boundaries along a heat path by using the linear intercept method, and then we're going to measure the thermal conductivity and see whether we see any effects. So we've used the laser flash method to do this. So here, this is another way to rewrite my simple model of thermal resistors in series. I've got basically the overall thermal conductivity written in terms of resistivity. I've got the single crystal thermal conductivity, and then I have an additional term for the grain boundaries. So N is the number of grain boundaries per unit length of heat path. What you can see here, this is the resistivity, and this is basically the number of interfaces per unit length, or grain boundaries. So this is large grains, small grains, okay? As we increase the number of grain boundaries, you can see that there is an overall increase in the thermal resistivity of the material. This is tin oxide. So Sylvie Grandjean knows this work rather well because she made these measurements and she's in the audience. What you will see is that we see this increase, and that from this rather simple expression, if we simply take the slope here, we can make an estimate of the grain boundary thermal resistance. And this gives us a value of the order of 10 to the minus 8 meters squared Kelvin per watt. We also notice that there is very little difference at different temperatures. So it seems that this value is approximately constant with temperature. Well, that's fine. It worked in tin oxide. Let's look at two different materials, alumina and magnesia. We get very similar behavior, a nice slope increase in thermal resistivity with an increase in the number of grain boundaries along the heat path, or going from large grains to small grains. We see a similar slope in magnesia, and again we have values of around 10 to the minus 8 meters squared Kelvin per watt. Okay? So I want just to retain this figure for the average value for the grain boundary thermal resistance. Now I'm going to look at porous ceramics. So if we look at a porous ceramic, we have a complex problem because we have the conduction in the solid skeleton, we have the effect of the grain boundaries, and then we have a possible parallel heat path through the gas, because the air, for example, will have a thermal conductivity. And then maybe there would also be, in a very porous ceramic, a possible radiation heat path. So it's a complex problem. Now, I'm going to look at basically two-phase models and indicate your interest in two of them in particular. We're going to start with, so here we're looking at effective thermal conductivity as a function of the pore fraction. We're going to look at Maxwell's model here, which is basically the model of a sphere inside a solid matrix. Okay? It's a two-phase problem, but we're going to take the case of a spherical pore here. So this describes rather nicely closed porosity, small amounts of closed porosity. So decrease of thermal conductivity as we increase the pore fraction. Now there's another very useful model, because when we make typical ceramics, the porosity if it's very dense, it's closed, but if it's more porous, let's say 50%, the porosity becomes connected or open. So this model would no longer seem to be appropriate. So for this situation, Landauer's effective medium expression is rather useful. This is based on basically taking equivalent pore volumes plus grain volumes of equivalent size and mixing them up with random positions. Okay? So this enables us to go to basically a situation with open porosity. So again, we see a decrease in thermal conductivity as we increase the pore volume fraction, but it is in fact actually steeper. And so this point here, about 15%, is giving you the transition between going from closed porosity to open porosity. Okay? You can see how the Maxwell's predictions and Landauer's predictions separate. So this we have found to be a very useful model. The other two models, well, this is Riley's model of a cylinder, which is in some situations could be useful, and this is a Hashon-Strickman lower bound limit. So this is somewhat hypothetical because here we have the solid particle surrounded by space. So here is the test of Landauer's expression on basically very porous stabilized zirconia, which has been made with a polymer pore forming agent. And you can see that the predicted curve gives very nice values compared to the experimental data. So this is obviously very encouraging. Let me show you a case where it didn't work quite so well. So again, this is Sylvie Grandjean who's responsible for this. Here we see Landauer's prediction, and here we see porous alumina, but which has a steeper dependence on the pore volume fraction. Well, in fact, the way these samples were made was in a very traditional ceramic way, taking a pressed powder compact and then playing around with the firing cycle. What we actually have are denser, larger grain ceramics, and here we have the more porous but smaller grain material. So in fact, there's a feature we haven't taken into account, and that is the role of a change in average grain size. So this affects the number of grain boundaries in the heat path. So what you can see here is that maybe we could explain this difference by the contribution of the grain boundaries. Well, we can in fact take this into account because this is Landauer's expression where you will see the pore volume fraction. You will see somewhere, if I can find it, here we are, the solid phase thermal conductivity, and then the conductivity of the pore phase. Well, we could actually adjust our thermal conductivity for the solid phase, the skeleton, by taking into account the grain boundaries. So this is what we have done for these three different situations, zirconia, alumina, and tin oxide, using our earlier values of grain boundary thermal resistance. So perhaps we can improve our model. So here you can see we've actually done two things. One, we've actually fixed the grain size by using starch casting. So these samples were made in Prague, in Willy Pap's group. And so this is fixed the average grain size not to vary with the preparation conditions. In other words, we've used the same firing cycle for all these samples, and the pore volume fraction has been varied by the amount of starch incorporated into the mixture to start with. And then we've worked out the average grain size from microscopy, and here you can see that, which means that we've corrected the value of the thermal conductivity, and we now get a very nice fit between our predicted curve and our experimental data. So, obviously, this is looking rather encouraging. So now I'm going to show you a case where things really did not work out, but this is perhaps explainable. Here we've gone on to more very porous alumina material. This is on a log scale. This is the pore volume fraction. So now on the log scale, Landauer's prediction is this curve here, and here we are at the percolation threshold. So you can see that there is a separation between the experimental points for these very porous materials with Landauer's curve. But then if you think about it, it actually seems rather reasonable, because obviously when we make ceramics, we like them to have a minimum of mechanical strength. So this means that if we want some mechanical strength, we have to have a continuous solid network. And Landauer's model is based on random grain positions. So at the percolation threshold, we would start cutting up this solid skeleton. And we don't make materials like this. So it's normal that this sort of very porous material, we start to see that the thermal conductivity is above Landauer's model because we have solid pathways. And these are obviously heat paths in the system. So in fact, what we do is we actually return towards Maxwell's model. Well, this was an attempt to do some numerical simulation on this. So, taking this idea that we actually need continuity in the solid skeleton in the material we make for mechanical strength, this actually leads us to the idea that if we're looking at thermal insulators, there is almost a sort of natural limit round about 0.1 watts per meter per Kelvin, where essentially this need for continuity stops us going to more thermally insulating material. So here I've just listed different materials, and you can see that though there is very high pore volume fraction, here we never achieve values lower than about 0.1 watts per meter per Kelvin, because we are going above Landauer's curve. So now I'm just going to take a rather interesting case where this idea is somewhat defeated. So I'm going to finish with 3 examples. And the first one is fibrous fumed silica compacts. So this has been made by Hiwaya Abe's group in Japan. And I believe there is an industrial product which gives a performance which is somewhat similar. The thermal conductivity of this material is about 27 milliwatts per meter per Kelvin, which is at room temperature, which is really very, very low, because the value of air is 26. So this is very performing material. So the question is, why is there such a low value? Well, let me not go too fast here. The first thing is that in this material, the overall pore volume fraction is about 80%. If I assume, it's made out of very fine silica particles. So let's say silica has a value of about 1 watt per meter per Kelvin, and that there are grain boundaries, because it's about 50 nanometers the grain size, every 50 nanometers. Well, this, using our previous expression, is sufficient to reduce the thermal conductivity to a value of about 0.8. But I have another very interesting feature in this material. So here we have an idea of the microstructure, is that there are rather small pores as well, of the order of about 100 nanometers. Now, the mean free path of air molecules is about 200 nanometers. So here, this means that an air molecule, nitrogen or oxygen, is actually going to hit the sides of the pore wall before it meets another air molecule. So this actually restricts the propagation of heat through the gas. So the effect of that is to reduce the thermal conductivity of the pore. So if you make very small pores, you can reduce the thermal conductivity of the gas inside this. This is a way of reducing thermal conductivity. And then finally, the system has glass fibers to make sure that it all holds together. Okay? So I'm going to take this value here, I'm going to take this value here, and I'm going to do something very simple. I'm going to apply Maxwell's model. Okay? If I do that, what it gives me is a value of about 0.15 watts per meter per Kelvin, which is nowhere near 27 milliwatts per meter per Kelvin. So I don't have enough of a model, even though I've taken into account a lot of interesting features. So second approach is to say, well, the role of the fibers could be to hold the system together and to allow the particles to adopt random positions. Okay? Well, if that's the case, we could then use Landauer's prediction. So this gives us a value, if we do that, of about 10 milliwatts per meter per Kelvin. So this is doing rather well. So it suggests that one of the important advantages of the fibers is we can allow the grains to adopt random positions and to break up some of the heat paths going through the solid network. Okay? Well, it's probably a lower limit because the solid matrix will be a little bit more connected than that. It's interesting to note that if I don't take into account a reduced value of thermal conductivity in the pores, my prediction would be 54 milliwatts per meter per Kelvin. So I can't just ignore the pores altogether. They seem to have a role according to these calculations. So this is an important aspect of nanostructure on the thermal properties of this particular system. Now, here is another interesting example from Bruno Verne's work in his thesis. He was working on incorporating, so this is no longer a porous system, it's the reverse idea. Instead of trying to make a very good thermal insulator, we're now trying to make a good heat conductor or thermal conductor. Okay? So the idea has been to use carbon nanotubes, okay, and incorporate them into an aluminum matrix. Theoretically, according to some people anyway, the nanotube has a value running along the axis, a value of 3,000 watts per meter per Kelvin. Well, that's very high because it's higher than the thermal conductivity of diamond. So even if we reason that there's the center of the affair which is missing in the nanotube, and we correct the value a little bit for this empty space here, this would give us an effective thermal conductivity of about 600 watts per meter per Kelvin. It's obviously interesting to try and incorporate these very highly conducting entities into an aluminum matrix if we want to improve the heat sinking characteristics of a substrate. So Bruno Verne in Limoges, working with Thierry Chartier and Fabrice Rossignol and the Toulouse group, incorporated some of these nanotubes in small amounts into an aluminum matrix. So there was various ways of techniques of making the material. The important aspect was to have what they described as a percolating network, in other words, a continuous solid path for the nanotube through the system. And to align these in a certain way. Now, the effect of making this system, so in fact it's not just one nanotube, but it's a collection of, or a bundle of carbon nanotubes. The effect of that was perhaps a little bit surprising to what they originally wanted to do. Here we have thermal conductivity, and here we have the volume fraction of the carbon nanotubes. As we increase the number of nanotubes, what we see is a decrease in the thermal conductivity, which is perhaps a little bit disappointing in this piece of work. So the very interesting thing that Bruno Verne did was to try to analyze the reasons behind, let's say, failure. The conclusions that we came to is that, okay, maybe we have a very highly conducting carbon nanotube in the system, but we have problems of poor thermal contact between the nanotube or the bundle of nanotubes with the alumina, and this is giving a very high internal thermal resistance. The radial here doesn't refer to the nanotube, but to disk samples. So in fact, if we consider the radial direction of the disk, the nanotubes are aligned in the radial direction. So when we look at the axial direction down the disk, in fact, this is across the direction of the nanotubes, and you see that there's an even stronger effect. So, problem of an interface between the nanotubes and the alumina, probably a problem of interfaces inside the fiber bundle, and basically what it's giving us is an insulating nanotube region inside the matrix, which has an orientating effect. So explaining these two different curves. So here, basically, other microstructural features are obscuring the advantage to be gained from the nanostructure. So just to finish, I want to mention some work from my own lab on clays. So Kyle in clays, so Thierry Epicier, I was rather pleased because he showed a nice diagram of a clay particle. Clays, well, we've been looking at the thermal properties of clays for various regions, and in particular the green bodies, so the pressed powder compacts. So I'll just remind you that a clay is a layered structure, okay, with a basic unit of a length of about 7-8 angstroms in the Carl-N8 form. Okay, we're going to look at its thermal conductivity. So here you can see the structure at a higher scale, where we have platelets, okay, so the platey structure. And if we go to an even larger scale, we have basically packing of the plates into grains. And so this is going to give us an interesting system. So there are many interfaces in the system. Here are our measurements on the pressed powder compacts at room temperature of the thermal conductivity. Well, the first thing that we've done is we've measured directly the thermal conductivity. Okay? So we have values which are very low, 0.17, 0.2, and then 0.5 in monmorillonite. These materials had, that's in French, they had rather high porosities. So what we've then done is we've used Landauer's model to predict our values of the solid phase. So this gives us still values of around 0.4 watts per meter per Kelvin, which is really rather low. Now for monmorillonite, we could actually explain the slightly higher value by the presence of quartz, which acts as conducting particles in the system. Okay? So I'm going to ignore this last line. Okay? So we basically have very insulating material. So since we have these very large number of interfaces, this low value, and we will also note that thermal conductivity is approximately constant with temperature, might be explained by the presence of all the interfaces and the fact that the thermal conductivity of a platelet is not too high. But basically it's the interfaces that control the affair. So this was our first hypothesis. Okay? Well, in fact, when we look at it, here we look at two different forms of Carl-N8 with different characteristic sizes. Okay, so the plates have got sizes either about 0.8 microns or 0.45 microns with slightly different thicknesses. Now, what's interesting is that the larger particles actually have the lower thermal conductivity. And so this puts a bit of a hole in our theory of the role of the interfaces controlling the affair. So we had to sort of think again. Basically, if we look at this expression, if it's not this term that's controlling the thermal conductivity, it then means it must be down to this term here, the intrinsic thermal conductivity, okay, of being of such a low value that it dominates this term. So what could be the reason for that? Well, the best reason that we can find is the fact, one, it must be a two-dimensional conductor. It's got a intrinsically a two-directional or a layer structure. So we would expect that in the AB planes, the thermal conductivity is higher than along the C-axis. And the second aspect is we have the interlayer in between each block of kaolin. And we think that here, it's this feature here, which is at the nanoscale, which is controlling the thermal conductivity of kaolin and making it very low. So this is what our conclusion has been, that the clay is basically a nanomaterial. And I think it's there that I will finish and just make a few concluding remarks. So first of all, for polycrystalline oxides, the average value of the thermal resistance of a grain boundary is around about 10 to the minus 8 meters squared per Kelvin per watt. If we want to describe in a porous ceramic the effect of the porosity, Landauer's model is very useful up to the percolation threshold of about 65%. After that, the need for continuity gives us a natural limit in the thermal conductivity of a porous material of about 0.1 watts per meter per Kelvin. Then we note in the very efficient thermal insulator there's an important but not the only role of the very small pores, which are less than 100 nanometers, which decrease the thermal conductivity of the gas in the pores to a low value. In the aluminum carbon nanotube composites, we had to be careful about other microstructural effects like interface effects, which obscure any benefits we might get from the nanostructure. And then finally, in kaolin, clay, we have a low value of thermal conductivity, which we could relate to the structure of the clay at the nanoscale. Thank you very much.